Okay, so the main research area is focused on the control systems, which contains usually a few control devices expressed by these pictures, and it depends from the company who use this software. Sometimes it's just one PLC equipped with the binary and digital input outputs, and sometimes it's nearly 10 and little more devices, which is equipped with more number of external inputs and outputs. In our work, we use different hardware and software architecture because we want to provide one environment for different manufacturers. So we have to deal with different processors, peripherals, runtimes, and even in the operating systems. We use desktop computer, which is performed for program developing, for control program developing. And this computer is equipped with our package CPDev, which allow for programming of distributed control systems. Typical applications are from the small controllers like soya milk factory in the Philippines, across to marine ships in the Netherlands, to the power plant in the Spain. So we have wide applications already working. How the software developing scenario looks, it usually starts in the code written in the ST language. And from this point, why ST? Because ST is defined in the standard. And the second reason, because our customers usually have some previous code written for different software, for different manufacturer, for different software. And it happens that these devices are already not produced, so they have to replace them, but they don't want to change the code or just want to do some minor improvements, not for writing the whole control system again. But going back to this code, and from this point, we have two tracks. The first one, we can provide translation to the code written in pure C language. There is a various number of tasks, so you can use some other operating software systems like Matiec's compiler, which is not our, but performs this translation. And from this code, you see by using design compiler, by using specialized compiler for the target platform, you can achieve binary form and target platform form. So this is a little bit longer step, which can be achieved without our solution. And our solution is by providing binary form, portable binary form, which be executed on the target platforms, which can be set up on each platform. So we provide one binary code for these platforms, and this code is generated by our compiler. This is a screenshot of our software. This is IDE of our software. We can see the project tree, the code industry, the debugging window, which shows the virtual machines integral commands. And now I will present target platforms, which we already developed. So from the beginning, we start on the x86 systems. Now we are using also x64 systems. But from the beginning, also we start with AVR processors. Some producers uses ARM, and similar. Technically, we are able to set up our virtual machine on any operating systems. Successfully, we already set up with Windows Embedded, FreeRTOS, Linux, or QNX systems. And we can also use our virtual machine, our prototype platforms, like Arduino, Nucleo, ASP32, and similar, which is presented here. This is the internal of the virtual machines. The virtual machine contains two main portions of code memory and data memory. Code memory contains the instructions, written in binary form. Data memory contains values for the processing. And also, our virtual machine is equipped with the instruction processing unit, which uses program counter, database register, and flash register, which will be used in the Denotational application. So going further, we use Vim's language. It's short from the virtual machine assembler. And this line is written in ST language. So it is a typical start-stop program, which updates the motor output depending on the start of the motor value. This ST code would be compiled to this intermediate form. So we see commands like jump 0, no jump 0, and data initialization, jump, and data initialization. Here we have a short, brief presentation of available instruction. Here we have some system procedures. This is a table which types we are handling in our virtual machine. Our virtual machine can be adjusted according to the needs of the target platform. So it doesn't happen that everything is applicable on each device. So we can configure our compiler by providing some descriptions which are stored in the LCF files, and we can present here how the bus width is, what is the size of the addresses, 2 bytes or 4 bytes. Because sometimes 2 bytes addresses are not enough. We can combine the whole machine using includes file. We can remove some types from the virtual machine. We can do new implementations here, aliases. We can define functions which are available in the virtual machine, and the system procedures which are also available in the virtual machine. So now I will switch to the main topic of the presentation, which is the Denotational semantic model. What is this? This is a formalized description of the virtual machines. It's based on the abstract map object, which assigns meanings to program. And we will see the following components which we presented in details. So we start from the semantic domains. Domains are used for, basic domains are used for deriving domain of the machine state. So we define subdomain like basic types, which is a union of the sets 1 byte, 2 bytes, 4 bytes. Similar is data chunks. Next one is address. Address varies because address size can be equal to 2, so there is 2 bytes or 4 bytes. Also, we have function memory, which is a function which takes address and return 1 byte. We have a code memory domain, which is the same as a memory domain. We have a stack domain, which is address, cleaner closure, and code stack, code registers, and flags. And the machine state is transformation of multiplication of the code memory, data memory, code stack, code register, data register, and flags. This is a Cartesian product of this data, of this domain. So here we have an access function, which is obvious because obtaining 1 byte memory from the address and the memory state, we receive 1 value. Also, we can take address to indicate the pointers, and updating memory, taking address memory and value to produce new memory. It will be expressed as the new object. Now we can see the idea of the instruction decoding. The instruction will combine from the group and the type. And first the machine checks the group and then it checks the type. And after that, it applies such repetitions, or updates the flags, which can be shown here. This is a lambda notation of any universal notation, any universal instruction, that for the input state, we can split them to the components and process like this, process according to these operations, and select the proper function. Using the proper function, we return a state which will be expressed by this one formula. So now the focus on the remas instruction of the formula. So for example, we have jump not zero command, which takes 2 operands, and after decoding the addresses, he takes the value from the 1 byte memory, this is control value, and after that is matching this control value to be true or false. If true, the return state will be expressed like this one. If the false, the return state will be expressed like this one, because the target address of the next instruction differs depending on the value of this conditional jump. Similar situation we have in the call-B instruction, which obtaining addresses and pushes the return values of the register from the additional. Okay, this code is this formula followed by the implementation and RCC, and here we can see that the call-B instructions, which are expressed in similar commands in the RCC, so we can derive from the formula just pure C for our virtual machine. To sum up, our Denotational model provides universal couple-independent virtual machine description. We can make a scalability of our virtual machine by LCFIs. And this formal semantic model is used to enhance the software quality. And this equitation are followed by C++ implementation. And this technique allows us for comparing the implementation with the expected behavior, also with the behavior of other systems. Okay, thank you for your attention.
Thank you very much for a very interesting presentation. I open the discussion. So we have no questions about us.
My question is as following. You are prepared any models and applications of one program for VMware, for other processors. Could you compare the results? What's the parameters of the products? I think about size of memory. What the differences between the applications on the other different processors?
Yeah, our solution is not quite big as VMware or similar, because we are not focusing on the virtual processing like this performed in the physical processors, but we are focusing, our virtual machine is a software. It's a software which executes special commands like Java and .NET, but it's more deterministic, because everybody complains that the Java cannot be used to the control systems because there is a garbage collector which runs anybody don't know when. So our system have no garbage collector, because control system doesn't like to grow and to shrink. So our system is fixed. Also this previous one written in the order of the ST standard, which was described in EIC 6113 standard.
Thank you very much.